Welcome to this quiet space, a place for gentle stories from the heart of science, designed to help your mind settle as you drift toward sleep. Tonight, we will begin a great journey together, a slow descent through stone and time to the very center of our own world, exploring the heart of the planet. I invite you to find a comfortable position, to let your breathing soften, and to allow these words to be a gentle guide into the wonders that lie deep beneath you. Before we begin, I would love to know where you are listening from tonight, what small corner of this beautiful world you call home. Please feel free to share in a comment below. And if you find a sense of peace here, please support our journey by leaving a like and subscribing to the channel. Your presence here is deeply appreciated. And so, our story begins, not with a great leap, but with a quiet feeling of stillness, the simple and profound sensation of the ground beneath you. Perhaps you can feel it now, through the layers of your home, the weight of your own body finding its rest upon the solid, unwavering presence of the earth. It is the most fundamental experience of our existence, this feeling of being held, of having a place to stand, a foundation upon which all of our lives are built. We walk upon it, we build upon it, we sleep upon it, and we trust it so completely that we rarely give it a second thought. This silent, patient floor of our world. Yet, this feeling of absolute solidity is a beautiful illusion, a gentle trick of scale that conceals a reality of unimaginable depth and dynamism. The ground we trust is not the end of the story, but merely the title page of a volume so immense and ancient that it defies our everyday comprehension. Let us begin our journey by simply adjusting our perspective, by zooming out from this familiar, solid ground, and allowing the true shape of our world to emerge in our minds. Imagine floating away from the surface, rising higher and higher, until the gentle curves of the horizon resolve into the perfect, marbled sphere of our planet hanging in the silent darkness of space. From this vantage point, we can begin to appreciate the true scale of the journey that awaits us. The distance from the surface where you are resting now, all the way down to the fiery center of the Earth, is approximately 6,371 kilometers. This is a number so large it feels abstract, so let us try to feel it differently. Imagine a single, impossibly fine thread, stretching from your feet, down through the entire planet to its core. If you were to travel along that thread, it would be a journey longer than a flight from London to Mumbai, a distance that speaks of planetary majesty. And it is down this thread that we will travel, not with drills or machines, but with the quiet power of scientific imagination, listening to the echoes and whispers that travel up from those impossible depths. The first layer we must pass through is the one we already know, the one we call home. The crust. It is the skin of our planet, the source of all our soil, all our mountains, all our ocean floors. Yet, from our cosmic perspective, we see it for what it truly is, an astonishingly, terrifyingly thin layer. If the Earth were the size of an apple, the crust would be no thicker than its delicate skin. This skin is not uniform. It has two distinct personalities. Beneath the great oceans, it is a thin, dark, and youthful layer of rock called basalt, often only 5 to 10 kilometers thick, constantly being born from volcanic ridges and recycled back into the depths. But under the continents, the land masses upon which we live, the crust is much thicker, lighter, and far more ancient. This continental crust, made of rocks like granite, can be anywhere from 30 to 70 kilometers deep, carrying within its structure the geological memories of billions of years of history. It is a mosaic of old mountain roots and ancient continental hearts, a complex and weathered foundation. But whether it is the young oceanic floor or the old continental land, it all rests upon something else entirely. This solid outer part of the Earth, containing both the crust and the very top, rigid layer of the next level down, is called the lithosphere. This is the great, brittle shell of our world, and it is fractured, broken into a dozen or so major pieces that float and drift upon the layer below. So the solid ground you feel is not a single, unbroken foundation, but more like a piece of an immense, shattered eggshell, moving with an imperceptible slowness upon a deep, hidden sea of yielding rock. And beneath that shell, the true journey begins. The vast majority of our planet is composed of two other realms, the mantle and the core. The mantle is a vast, dark expanse of silicate rock that makes up over 80% of the Earth's volume, a place of immense pressure and slowly churning heat that extends nearly halfway to the planet's center. And at the very heart of it all lies the core, a sphere of incandescent metal, a world within a world divided into a liquid outer sea and a solid, crystalline center. These are just names for now, labels on a map of a place we have never seen. But they are the chapters of our journey, destinations in a land of pure inference and imagination. We know of them not by sight, but by listening. We have mapped this invisible, interior world by tracking the journey of seismic waves from distant earthquakes, observing how they bend, reflect, and change speed as they pass through these different layers. These planetary vibrations are our eyes and ears, painting a picture of the deep earth with the language of echoes. As we prepare to take our first step down, leaving the familiar skin of the world behind, let us hold on to this image. Our entire world, all of our continents and oceans, all of our history and our future, resting upon this impossibly fragile skin, a luminous, living surface that separates the light of the sun from the ancient, fiery darkness of the deep. And this thin, delicate skin is not still, for it is constantly breathing with a rhythm so slow that a human lifetime is too short to perceive even a single breath. The great, fractured plates of the lithosphere are in constant, silent motion, drifting across the face of the globe at about the same speed that your fingernails grow. This is the grand and elegant theory of plate tectonics, the discovery that our seemingly static world is, in fact, a dynamic and restless mosaic. Imagine looking down upon the Earth and seeing these continental and oceanic plates not as solid, immovable rock, but as colossal ice flows on a dark, slow-moving river. Some are grinding past each other, creating vast fault lines. Some are colliding, crumpling their edges to raise majestic mountain ranges that pierce the sky. And in other places, they are pulling apart, allowing new crust to be born from the fiery mantle below in the abyssal depths of the ocean. This continuous, silent dance is the engine of our planet's surface, the force that shapes our landscapes, directs our climates, and builds the very ground upon which we live. These plates, these colossal dancers, are not all the same. We spoke of their two personalities, and this difference is the key to their grand performance. The floor of the oceans is made of dense, heavy basalt, a dark volcanic rock. Because it is so dense, it rests lower than the continental crust, creating the great basins that hold our world's water. The continents, on the other hand, are made of lighter, less dense rocks, like granite. They are like great, buoyant rafts of stone, floating higher on the underlying mantle. This difference in density is why the world is not a uniform, water-covered sphere. The light continents rise above the global sea level, providing a stage for the evolution of terrestrial life. And they are ancient. While the ocean floor is constantly being created and destroyed in a cycle that lasts only a couple of 100 million years, some parts of the continental crust are nearly as old as the planet itself, containing rocks that are 4 billion years old. They are the great, weathered archives of our world, carrying the memory of deep time in their crystalline structures. This slow, inexorable movement of the continents means that the map of our world is not a permanent fixture. It is a single frame in a magnificent, planetary film. If we could rewind this film, speeding up time so that 1 million years passed in a single second, we would see the continents waltz across the globe. We would see India, once a separate island, crashing into Asia to create the Himalayas. We would see the Atlantic Ocean opening like a zipper, pushing the Americas away from Europe and Africa. And if we went back far enough, around 250 million years ago, we would witness a world that is almost impossible for us to imagine. A world with one ocean and one single, colossal supercontinent. Geologists call this ancient landmass Pangaea, a Greek word meaning all the earth. In this lost world, the east coast of what is now North America was nestled against the shoulder of Africa, and Antarctica was connected to Australia, warm and forested. It is a profound and humbling thought that every continent, every nation, every place we call home, was once part of a single, unified land, a shared planetary heritage that was fractured and scattered by the slow, powerful currents of the deep Earth. The memory of this unity is written in the rocks, in the fossil records that match across vast oceans, and in the coastlines that still look like they could fit together like pieces of a cosmic puzzle. Our journey downwards, then, must begin by crossing the first true boundary, the invisible floor that lies beneath the crust we call home. This boundary has a name. It is called the Mohorovičić discontinuity, or the MOHO for short. It was discovered not by digging, but by listening. In the early 20th century, a Croatian seismologist named Andrija Mohorovičić was studying the shockwaves from an earthquake. He noticed something peculiar: seismic waves that traveled deeper into the earth before returning to the surface actually arrived sooner than those that had traveled a shorter, more direct path through the crust. This could only mean one thing. At a certain depth, the waves had entered a new medium, a new kind of rock so fundamentally different that it allowed the waves to travel significantly faster. He had discovered the base of the crust. The MOHO is not a physical line you could see or touch, but rather a profound change in the physical properties of our world. It is the place where the familiar granites and basalts of the crust give way to the dense, olivine-rich rock of the mantle. It is a transition that occurs on average about 35 kilometers beneath the continents, and only about 7 kilometers beneath the ocean floor. To cross this boundary in our minds is to leave the surface world behind entirely, to enter for the first time into the vast, hidden immensity of the mantle, the true interior of our planet, a place governed by pressures and temperatures that have no equivalent on the sunlit skin of the world. Beneath the quiet surface of the world, this slow and ceaseless motion of the continental plates generates a tension that is almost beyond our ability to conceive. A gradual accumulation of planetary stress along the vast, fractured edges where the plates meet. For centuries, for millennia, they push and grind against one another in utter silence, the pressure building degree by imperceptible degree. And then, in a single moment, the tension becomes too great, the friction gives way, and the stored energy is released in a sudden, violent shudder that propagates through the very fabric of the planet. This is the genesis of an earthquake, the most dramatic and immediate expression of the deep Earth's restlessness. These moments are where the planet speaks, where its immense power is made manifest on the surface. The interactions at these great seams, these plate boundaries, take on different forms, like a conversation with a vast and varied vocabulary. Where plates pull away from each other, as they do along the mid-Atlantic ridge, new Earth is born as magma. From the mantle rises to fill the gap, creating a continuous volcanic seam on the ocean floor. Where they slide past one another, like along the San Andreas Fault in California, they create a landscape of sheared rock and stored tension, waiting for its next release. And most dramatically, where plates collide, the world is remade. When a dense oceanic plate meets a buoyant continental plate, the heavier ocean floor is forced to bend and slide downwards, a process of descent known as subduction, plunging back into the hot mantle from which it once came. As it descends, it carries water down with it, which lowers the melting point of the surrounding mantle rock, creating plumes of magma that rise to the surface and erupt, forming chains of volcanoes along the edge of the continent. This is why the coasts of South America are lined with the Andes, a spine of fire and rock born from a collision that has been unfolding for millions of years. These volcanoes are more than just mountains that erupt. They are precious, fiery messengers from the world below. They are the Earth's most direct form of communication, windows into the chemistry and character of the upper mantle. The lava and gases that emerge from them are physical samples of this inaccessible realm, fragments of the deep brought into the light, which we can analyze in our laboratories to understand the composition of the planet's hidden layers. In this way, every eruption is a revelation, a page of the Earth's autobiography, written in fire and stone. Nowhere is this fiery conversation more articulate than around the basin of the Pacific Ocean. Here, the vast Pacific plate is grinding against several surrounding plates, creating a nearly continuous ring of subduction zones and volcanic arcs that stretches for over 40,000 kilometers. This is the famed Ring of Fire, a vast planetary necklace adorned with hundreds of active volcanoes and responsible for roughly 90% of the world's earthquakes. It is a place where the skin of the earth is thin and the breath of the mantle is hot, a constant reminder of the immense, molten engine that churns beneath the placid blue of the world's largest ocean. To trace its path is to take a tour of the planet's most dynamic regions, from the tip of South America up through Central America and North America's west coast, across the Aleutian Islands of Alaska, down through Japan, the Philippines, and Indonesia, and into New Zealand. It is a testament to the fact that the Earth is not a cold, dead rock, but a living, breathing, and profoundly powerful system. But the most profound messages from these deep stirrings are not the ones we can see, but the ones we can only feel, or rather, detect with our most sensitive instruments. Every time there is a slip along a fault line, whether it is a tiny tremor or a great earthquake, it sends vibrations, or seismic waves, radiating out in all directions, just as a pebble dropped in a still pond creates ripples that travel to the farthest shore. These waves travel not just across the surface, but through the entire body of the Earth, carrying with them a story of every layer they pass through. There are two main types of these bodily waves, two primary voices in the Earth's deep song. The first are called primary waves, or P waves, because they are the fastest and the first to arrive at any listening station. They are compression waves, meaning they travel by pushing and pulling the rock in the same direction they are moving, like a pulse traveling down a slinky spring. They can move through both solids and liquids, a whisper that travels ahead of the main event. Following behind them are the secondary waves, or S waves. These are slower, and they move the rock particles up and down or side to side, perpendicular to their direction of travel, like a wave you might make by shaking a rope. This shearing motion means S waves can only travel through solid material. They are stopped dead by any liquid they encounter. These two signals, the push of the P wave and the shake of the S wave, are the fundamental letters in the alphabet we use to read the planet's interior. They are the echoes from which we have built our entire understanding of the world that waits beneath our feet. These seismic waves, born from the sudden release of ancient tensions, radiate outwards as perfect, expanding spheres of energy, beginning their silent journey through the heart of the planet. On the surface, our seismographs listen, like a global network of ears pressed to the ground, patiently waiting for these faint, coded messages to arrive from the depths. And it is by listening to these messages, by following their paths, that we can finally leave the crust behind and begin our descent into the Earth's next great realm, the mantle. The Moho boundary, which we have just crossed, is but the threshold to a kingdom of almost incomprehensible scale. The mantle is a vast, dark, and utterly silent cathedral of rock, a layer nearly 2,900 kilometers thick. If you think again of the Earth as a peach, we have spent our journey so far exploring only its thin, textured skin. Now, we are entering the thick, dense flesh that makes up the overwhelming majority of the fruit's substance. More than 80% of our planet's volume is here, in this immense and hidden world that separates the thin, living crust from the fiery metallic core. The nature of the mantle is one of the great paradoxes of our world. It is, for all intents and purposes, a solid rock. If you could hold a piece of it in your hand, it would feel as hard and unyielding as any stone you have ever touched. And yet, over the vast timescales of geology, this solid rock flows. This property is known as plasticity, the ability of a solid to deform and move without breaking. Imagine a block of very hard wax or a river of asphalt on a cold day. It appears perfectly solid, but over months or years, under the steady pressure of its own weight, it will slowly slump and flow. The mantle is like this, but on a scale of millions of years. Under the immense heat bubbling up from the core and the crushing pressure from the weight of the planet above, the solid rock of the mantle churns in vast, slow-motion currents, rising where it is hot and sinking where it is cool. These currents, moving slower than the growth of a tree, are the deep, hidden engine that drives the dance of the continents on the surface above. They are the river of stone upon which the pieces of our world float. This flowing rock is made of minerals that are familiar to us in chemistry, but exist under conditions that are entirely alien. It is composed primarily of silicates, compounds of silicon and oxygen, bonded with heavy elements like iron and magnesium. If we were to see it, much of the upper mantle would be a deep olive green, coloured by its dominant mineral, olivine. But as we descend deeper, the pressure begins to build to an astonishing degree, squeezing the very atoms of these minerals into new and more compact crystalline structures, transforming them into different materials with different properties. So the mantle is not a uniform sea of rock, but a layered and complex place, with its own internal weather and currents, its own geography of sinking slabs of old ocean floor and rising plumes of superheated rock. It is a dynamic world, not a static one, filled with a slow, powerful life of its own. But how can we possibly know this? How can we map the currents of a river of stone thousands of kilometers beneath our feet? We do it by listening to the P waves and the S waves. We use the entire planet as a kind of medical imaging device, a process called seismic tomography. It works in a way that is beautifully simple in principle. The speed at which seismic waves travel through rock depends on the rock's temperature and density. They travel faster through colder, denser rock, and slower through hotter, more buoyant rock. So, when a large earthquake occurs, say, in Indonesia, we can precisely time how long it takes for its P waves and S waves to arrive at seismographs all across the globe in South Africa, in Brazil, in Iceland. If the waves arrive at a station a little bit earlier than expected, we know that somewhere along their path from the earthquake to the station, they must have travelled through a region of the mantle that is unusually cold and dense. If they arrive a little bit late, their path must have crossed a plume of unusually hot rock. By combining the data from thousands of earthquakes, recorded at thousands of stations over many decades, scientists can build a stunning, three-dimensional map of the mantle's interior. It is the geological equivalent of a CAT scan, using the Earth's own vibrations to illuminate its hidden anatomy, revealing a breathtaking world of vast, sinking blue sheets of cold, subducting crust and great, rising red pillars of hot mantle plumes, a silent, majestic ballet that has shaped our world for billions of years. This silent, majestic ballet that seismic tomography reveals to us, this slow and unending dance of hot and cold rock within the deep earth, is the physical process of convection. It is, in its essence, the planet's way of breathing, of circulating its own internal heat, and it is perhaps the most important process happening on our world, for it is the unseen engine that drives nearly everything we experience on the surface. The principle is as simple and as elegant as the gentle simmering of a pot of water on a stove. The heat source at the bottom of the pot, like the immense heat radiating from the Earth's core, warms the layer of water just above it. As this water warms, it expands and becomes slightly less dense than the cooler water above it, and so it begins to rise. When it reaches the surface, it releases its heat into the air, cools, becomes denser again, and gently sinks back down to the bottom to be reheated, completing a slow, circular journey known as a convection current. Now, imagine this simple, looping dance scaled up to the size of a planet. The fluid is not water, but solid rock that flows on a timescale of eons. The heat source is not a simple flame, but the primordial fire of a planet's birth and the steady, gentle warmth of radioactive decay. This is mantle convection, a vast, planetary system of rising and falling rock, turning over and over in a cycle of profound and patient slowness. It is difficult to truly feel the timescale of this engine. For a single piece of rock to make the full journey to rise from the depths of the lower mantle, to travel along the underside of the lithosphere, and to sink once more as part of a cold, subducting slab can take hundreds of millions of years. This is a rhythm so slow that the entire history of humanity is but a fleeting, insignificant moment in one of its cycle. The continents themselves, which feel to us like the very definition of permanence, are merely carried along on the backs of these currents, their slow dance across the globe dictated by the rising and falling tides of this deep, hidden river of stone. Without this constant, churning motion, the Earth's interior would have cooled and solidified billions of years ago. Plate tectonics would have ceased, volcanoes would have fallen silent, and the planet may well have become a static and sterile world like Mars. It is this undying, slow-turning engine that has kept our world geologically alive, constantly renewing its surface, regulating its climate, and creating the dynamic conditions necessary for life to flourish and evolve. The flow within this global engine is not always a simple, uniform circulation. In certain places, exceptionally hot and buoyant, plumes of rock can rise from the deepest parts of the mantle, near the boundary with the core itself. These are called mantle plumes, and they are like narrow, focused jet streams of heat, ascending through the entire mantle to the surface. When one of these plumes reaches the base of the lithosphere, it creates a long-lived volcanic center known as a hotspot. Unlike the volcanoes that form at the edges of tectonic plates, these hotspots are stationary, for they are rooted in the deep mantle, far below the drifting continents and oceans. The most beautiful and famous example of this phenomenon on Earth is the Hawaiian island chain. The Pacific plate is slowly but steadily drifting towards the northwest, moving over a stationary hotspot that has been active for tens of millions of years. As the plate moves, the hotspot acts like a cosmic blowtorch, periodically punching through the crust to create a new volcano. This volcano then rises from the seafloor, builds itself into an island, and then, as the plate continues to carry it away from the hotspot, it goes extinct and begins its long, slow process of eroding back into the sea. You can read this history in the islands themselves. The oldest islands in the chain, to the northwest, are now little more than submerged seamounts, worn down by millennia of wind and waves. The younger islands, like Oahu and Maui, are lush and eroding, while the youngest island, the big island of Hawaii, is still being actively built, with fresh lava flows from the Kilauea volcano, adding new land to its shores. And even now, a new volcanic seamount is forming on the ocean floor to the southeast. The next Hawaiian island in the making, waiting for its turn to rise above the waves tens of thousands of years from now. This elegant chain of islands, stretched across the Pacific like a string of jewels, is the living, breathing proof of this deep earth process. It is the visible trace of an invisible plume, the direct connection between the sunlit world of swaying palms and the silent, churning darkness of the planetary engine, 2,900 kilometers below. It is a reminder that the most solid ground we know is simply a temporary stopping point on a much grander journey, powered by the slow, warm heartbeat of our planet. To continue our journey is to descend even further into this great, slow-turning engine, to travel deeper into the mantle, where the pressures and temperatures grow to levels that begin to warp the very nature of matter itself. As we move below the upper mantle, the realm that feeds the volcanoes and hotspots we know, we enter a strange and complex region known as the Mantle Transition Zone. This is not a simple boundary, but a distinct layer in our planet's interior, a stratum that lies between roughly 410 and 660 kilometers beneath our feet. From the surface, this region appears as a blank space on our maps of the interior, but to the seismic waves that pass through it, it is a place of profound and abrupt change. Seismologists noticed long ago that as the waves enter this zone, their speed suddenly jumps, indicating they have entered a material that is significantly denser than the rock above it. This zone is a planetary threshold, a place where the familiar rules of geology are left behind, and we enter a realm governed by the extraordinary physics of high pressure. The secret to the transition zone's strangeness lies in a process called a phase transition. The immense pressure in this part of the mantle, hundreds of thousands of times greater than the atmospheric pressure we experience on the surface, becomes so powerful that it can physically crush the crystalline structure of minerals, forcing their atoms to reconfigure themselves into new, more compact arrangements. Imagine you are building a structure with a set of toy blocks. You might have a sprawling, open design, but if you were asked to fit that same set of blocks into a much smaller box, you would have to find a new, denser way to pack them together. This is precisely what happens to the minerals in the transition zone. The most common mineral of the upper mantle, the green olivine, cannot withstand these pressures. At a depth of 410 kilometers, its atomic structure spontaneously collapses and rearranges to become a new mineral, a denser blue material called wadsleyite. And then, as we descend even deeper, to around 520 kilometers, the pressure crushes it again, and it transforms once more into an even denser mineral called ringwoodite. These are not chemical changes, the elements are still the same. This is a physical rebirth, matter itself being remade under the planet's colossal weight. This deep earth alchemy, this realm of crushed and reborn jewels, holds one of the most astonishing secrets of our planet. For a long time, scientists wondered how much water was cycling through the deep earth. They knew that water was carried down into the mantle at subduction zones, trapped in the minerals of the ocean floor. But where did it go? The answer, it seems, lies locked inside the crystal structure of ringwoodite. In recent years, by studying tiny samples of this mineral found inside diamonds that were brought to the surface by volcanic eruptions, and by recreating the conditions of the transition zone in laboratories, scientists made a breathtaking discovery. The crystalline lattice of ringwoodite is perfectly structured to trap and hold vast quantities of water, not as liquid, not as ice, not as vapor, but as hydroxide ions, an integral part of the mineral itself. The quantities are almost unbelievable. It is now estimated that the mantle's transition zone may hold more water than all of the Earth's oceans, rivers, and glaciers combined. A vast, hidden planetary reservoir locked away in a layer of blue, high-pressure stone. This hidden ocean is not one we could ever sail upon, but its presence profoundly affects the dynamics of the mantle, lubricating the flow of rock, and perhaps providing the source for the very water that fills the oceans on the surface. As we sink past this watery crystalline layer, we approach the very bottom of the mantle, and the world becomes stranger still. The last few hundred kilometers above the core form a complex and turbulent boundary layer that seismologists call the double prime layer. This is one of the most mysterious and dynamic places on the planet. It is a kind of planetary sediment, a graveyard where the cold, dense slabs of subducted oceanic crust may finally come to rest after their long journey down through the mantle. Here, they lie upon the searing hot boundary of the liquid outer core, and the incredible temperature difference between the two realms creates a place of intense chemical reactions and unpredictable behavior. It is a thermal and chemical borderland, where the mantle rock is heated to its limits, perhaps partially melting, and giving birth to the great mantle plumes that rise all the way to the surface. It is the final, chaotic shore of the rocky world, the last layer of the silicate mantle before we take the final plunge, across the most profound boundary in the entire planet, and into the incandescent, molten ocean of the Earth's metallic core. Leaving behind the strange, transitional shore of the double prime layer, we now take the final and most profound step of our descent, crossing a boundary that represents the single greatest change in the state of our world. We have travelled for nearly 3,000 kilometers through a realm of solid, silicate rock, but now we arrive at a frontier so sharp and so absolute that it is like stepping from a continent into an ocean. This is the Gutenberg discontinuity, named after the seismologist who discovered it, and it marks the bottom of the mantle and the top of the Earth's core. To cross it is to leave the world of stone behind and to enter a new world of liquid metal, a realm of such extreme temperature and pressure that it almost belongs to the realm of stars rather than planets. Here, in the silent, crushing darkness of the planet's center, lies a vast and turbulent ocean, an incandescent sphere of molten iron and nickel that churns with a power that will shape the fate of the entire world above. This outer core is an ocean in the truest sense of the word, but it is a sea unlike any we could ever imagine. It is not made of water, but of liquid iron, mixed with about 10% nickel and a few other lighter elements, like sulfur and oxygen, whose presence slightly lowers the mixture's melting point. It is a sphere of fluid metal more than 2,000 kilometers thick, a volume so great that you could fit the entire planet Mars within it. And it exists in a state of perpetual, violent motion, stirred by the planet's rotation and by its own internal heat, creating vast, swirling eddies and powerful currents that move at perhaps a few kilometers per year, a blistering speed compared to the glacial pace of the mantle above it. To picture it is to imagine a dark, luminous, and impossibly dense sea, not reflecting light, for there is none, but glowing with its own inner heat, a black body radiation that would be blindingly bright if only an eye were there to see it. The conditions in this hidden ocean are staggering, a physical reality pushed to its absolute limits. The temperatures here begin at around 4,000 degrees Celsius at the top of the core, and likely increase to over 5,000 degrees as we descend, a heat that is comparable to the surface of the Sun. The pressure is equally extreme, starting at over 1 million times the atmospheric pressure at the surface, and increasing to over 3 million atmospheres at its base. This pressure is so immense that it changes the very properties of the iron, but it is not yet enough to force it into a solid state. It remains a roiling, electrically conductive liquid, a metallic sea trapped within a rocky shell. These are numbers, but they represent a physical state that is almost mythological in its intensity, a place where the weight of a world crushes down upon a captive star, creating the heart of our planet. For a long time, the existence of this liquid ocean was a matter of pure theory, a logical deduction about how a planet should form and cool. But we know it is there with absolute certainty, thanks once again to the patient, coded messages of seismic waves. We know this ocean is liquid because of a profound silence, an immense shadow cast through the heart of the world. As we learned, the shearing S waves cannot travel through a liquid. Their side-to-side shaking motion is absorbed, dissipated by the fluid medium. Because of this, whenever a large earthquake occurs, there is a vast zone on the opposite side of the planet where the S waves are never detected. A seismograph placed in this S-wave shadow zone will record the arrival of the push-pull P waves, which can travel through the liquid core, but it will never feel the shake of the S waves. They are simply gone, blocked by the molten sea. This global shadow is the definitive proof of the outer core's liquid nature. It is the silhouette of a hidden ocean, a negative image that allows us to see an unseen world, a turbulent, metallic heart whose ceaseless motion holds the key to the survival of all life on the sunlit surface, far, far above. We find ourselves floating now in this turbulent, metallic sea, this vast ocean of liquid iron and nickel churning in the absolute darkness at the center of the world. It is a place of unimaginable violence and power, a self-sustaining furnace driven by heat and rotation. And one might wonder what the purpose of such a magnificent and hidden engine could possibly be. The answer is that the ceaseless motion of this subterranean ocean is responsible for creating one of the most important and beautiful features of our planet. A silent, invisible force field that protects us all, a luminous shield that has allowed life to flourish. For the churning of the outer core is the source of the Earth's magnetic field. This process, known as the geodynamo, is one of the most elegant and consequential in all of planetary science. As the hot, liquid iron rises, cools, and sinks in great convective columns, and as these columns are twisted and sheared by the rotation of the Earth, this motion of a conductive fluid creates colossal electrical currents. And a fundamental law of physics states that moving electrical currents generate magnetic fields. In essence, the outer core is a naturally occurring, self-sustaining electromagnet of planetary size. The electrical currents generate the magnetic field, and the magnetic field, in turn, influences the flow of the liquid iron, which reinforces the currents. It is a continuous feedback loop that has been running for at least 3.5 billion years, turning our Earth into a giant, if somewhat messy, bar magnet. This field is not confined to the planet's interior. It extends far out from the surface, creating a vast, protective bubble around our world called the magnetosphere. This invisible shield is not a perfect sphere. Instead, it is shaped by a constant, unending assault from our own sun. The sun continuously emits a stream of high-energy charged particles, mostly electrons and protons, known as the solar wind. This wind blows through the solar system at hundreds of kilometers per second, and it is this wind that compresses the magnetosphere on the side, facing the sun, and stretches it out into a long, teardrop-shaped tail on the night side, a tail that extends for millions of kilometers, far beyond the orbit of the moon. The importance of this luminous shield cannot be overstated. It is the silent, unsung guardian of life on Earth. Without the magnetosphere, the relentless solar wind would slam directly into our atmosphere, and over millions of years, it would strip it away, molecule by molecule, just as it is believed to have done on Mars after its own geodynamo died. Our oceans would boil away into space, and the surface of the planet would be sterilized by a constant bath of deadly cosmic radiation. It is the magnetic field, born from the churning of an ocean of metal 3,000 kilometers beneath our feet, that stands between us and a barren, lifeless fate. It deflects the vast majority of the solar wind around our planet, preserving our precious atmosphere and protecting the delicate chemistry of life from the harshness of space. Every breath you take is, in a very real sense, made possible by the unseen dance of liquid iron in the heart of the world. And sometimes, under the right conditions, this invisible guardian makes its presence known in the most spectacular and ethereal way possible. While the magnetosphere deflects most of the solar wind, some particles become trapped, spiraling along the magnetic field lines. These lines curve down towards the Earth at the north and south magnetic poles. As these trapped, high-energy particles are funneled down into the upper atmosphere near the poles. They collide with atoms of oxygen and nitrogen. These collisions excite the atmospheric atoms, giving them a surplus of energy, which they then release in the form of tiny flashes of light. When this happens on a colossal scale, with billions upon billions of particles streaming into the atmosphere, these tiny flashes merge into a breathtaking celestial display. The aurora borealis in the north, and the aurora australis in the south. These shimmering curtains of green, red, and violet light, dancing silently in the cold polar night sky, are a direct and visible manifestation of the Earth's magnetic field at work. They are the beautiful, ghostly evidence of our planet's invisible shield protecting us, a light show powered by the violent, churning heart of our world. This luminous, protective shield, whose visible breath we see in the dancing lights of the aurora, feels like one of our planet's great constants, a reliable and steadfast guardian. We learn from a young age to trust the compass, to believe that its needle points to a fixed and dependable north. Yet, the very same geodynamo that creates this field is a chaotic and turbulent engine, and the magnetic field it generates is anything but stable. It is a restless, shifting entity, a wandering ghost within the planetary machine, whose sense of direction is written not in stone, but in flowing, liquid metal. The first clue to this restlessness is the simple fact that the magnetic poles and the geographic poles are not in the same place. The geographic poles are the fixed points at the top and bottom of our planet, the ends of the axis around which the Earth spins. The magnetic poles, however, are the points where the magnetic field lines plunge vertically into the planet, and they are constantly on the move, drifting in response to the unpredictable eddies and currents in the outer core far below. This movement is called magnetic polar wandering, and for most of history, it was a slow, subtle drift. But in recent decades, this wandering has accelerated dramatically. The North Magnetic Pole, which for centuries had meandered slowly around the islands of northern Canada, has begun to race across the Arctic Ocean towards Siberia at a speed of up to 55 kilometers per year. This is a direct, surface-level manifestation of the dynamic, changing nature of the deep Earth. It is as if we can feel the quickening of a current in that hidden metallic sea, a subtle shift in the balance of the geodynamo that is pulling the field with it. This wandering is not a cause for alarm, but a profound reminder that we live on a world that is fluid and alive, from its molten heart to its shimmering, invisible shield. The compass is not a guide to a fixed point, but a tool that helps us orient ourselves within a force field that is constantly, slowly, breathing and shifting with the planet itself. But this gentle wandering is only the mildest expression of the geodynamo's chaotic nature. The geological record, written in the memory of ancient rocks, tells us that the magnetic field is capable of something far more dramatic, a complete and total reversal of its polarity. For reasons that are still not fully understood, but are likely related to the chaotic fluid dynamics within the core, the geodynamo can sometimes become unstable. During these times, the magnetic field can weaken significantly, perhaps to only 10% of its current strength. The well-defined north and south poles may vanish, replaced by a complex and messy field with multiple, weaker poles scattered across the globe. This period of instability might last for several thousand years, and then, as the geodynamo reorganizes itself, it settles back into a stable configuration. But with its polarity flipped, the magnetic pole that was once north would now be south, and the pole that was south would be north. An ancient compass needle would have pointed in the completely opposite direction. We know this has happened hundreds of times throughout our planet's history because of a remarkable field of study called paleomagnetism, which reads the fossilized magnetism locked within rocks. When molten rock, such as lava from a volcano, cools and solidifies, tiny, iron-rich mineral grains within it, such as magnetite, behave like microscopic compass needles. As the rock cools past a certain temperature, these tiny minerals align themselves with the direction of the Earth's magnetic field at that moment in time. And when the rock becomes fully solid, this magnetic orientation is frozen in place, preserved for millions or even billions of years. By studying layers of volcanic rock from different eras, scientists can read this magnetic history layer by layer. They find long periods where the magnetic field was oriented as it is today, which they call normal polarity, followed by layers where the field was completely reversed. This record, meticulously pieced together from rocks all over the world, creates a kind of geological barcode, a timeline of magnetic reversals stretching back through deep time. It is a stunning chronicle of a planet whose most fundamental directional force is not a constant, but a fluctuating, dynamic process, a testament to the beautiful and unpredictable heart of our ever-changing world. This image of a chaotic, churning, and ever-reversing ocean of liquid metal might suggest that the heart of our world is a place of pure, untamed turbulence. And for thousands of kilometers, it is. But our journey is not yet complete. For suspended in the very center of this violent, molten sea, there is one final realm, an anchor of profound stability and stillness, a world within a world that marks the true heart of our planet. As we descend through the liquid outer core, the temperature and pressure continue to rise to values that are almost beyond imagination. And just when it seems the conditions could not get any more extreme, we arrive at one last, subtle boundary. This is the Lehmann discontinuity, named for the pioneering Danish seismologist Inge Lehmann, who discovered it in the 1930s. While studying the seismic waves from a large earthquake, she detected faint P-wave echoes that should not have been there, signals that suggested the waves were reflecting off of something solid at the very center of the Earth. Her meticulous work revealed the existence of an inner core, a solid sphere floating in the middle of the liquid outer core. This is the final destination of our long journey, the Earth's inner core. It is a sphere of mostly iron and nickel, with a radius of about 1,220 kilometers, making it roughly 70% the size of our moon. And it is a place of the ultimate paradox. It is, by far, the hottest part of our planet, yet it is completely solid. The reason for this lies in the final, titanic battle between temperature and pressure. The heat in the inner core is staggering, with modern estimates placing it at around 6,000 degrees Celsius, a temperature that is hotter than the visible surface of the sun. At such a temperature, iron should, by all rights, be a gas, let alone a liquid. But the pressure at the center of our world is the most powerful force in the planet. The weight of all the overlying layers, the mantle, the crust, and the entire liquid outer core presses down on this central sphere with a force of over 3.6 million times the atmospheric pressure at sea level. This colossal pressure is so great that it physically squeezes the atoms of iron and nickel together, preventing them from breaking their bonds and flowing as a liquid. Even though they are vibrating with an incredible amount of thermal energy, they are locked into a fixed, crystalline lattice, forced into a solid state against their fiery will. You can imagine it like a crowd of people packed into a very small room. Even if everyone has the energy to run around, the sheer density of the crowd prevents anyone from moving. In the same way, the pressure at the Earth's center triumphs over the temperature, forging a solid sphere of metal in the heart of a stellar furnace. This is the incredible, solid star at the center of our world, a place where the laws of matter behave in ways we can only begin to simulate in our most advanced laboratories. And so, we have finally arrived. After a journey of more than 6,000 kilometers, from the gentle, sunlit surface to this place of impossible force, we find ourselves at the heart of the matter. We are in a silent, solid world, a single colossal crystal of iron, glowing with a heat that drives the entire planetary engine around it. It is the gravitational anchor of our world, the ultimate source of the heat that powers the geodynamo, the seed from which the entire layered structure of our planet grew. To be here, in our imaginations, is to reach a place of ultimate stillness and permanence, a silent, incandescent heart that has been suspended in this crushing darkness for billions of years. It is the final, quiet truth of our planet, a solid sun that will never be seen, but whose existence makes everything else possible. We have arrived at what feels like the end of the line, the final, solid ground at the heart of our world, a place of immense heat held in a state of perfect, crystalline stillness by even more immense pressure. It feels like an anchor, the unmoving center around which everything else revolves. And yet, the deeper that we listen to the faint seismic whispers that have guided us this far, the more we learn that even this solid heart has its own profound and mysterious dynamism. The inner core, this seemingly static sphere, is not locked in place with the rest of the planet. It is a world with its own independent rhythm. For decades, seismologists have been meticulously tracking the paths of seismic waves that travel directly through the inner core from one side of the Earth to the other. And in doing so, they discovered something that at first seemed impossible. The travel times were changing. Waves from repeating earthquakes, following the exact same path through the mantle and outer core, were completing their journey through the inner core, a fraction of a second faster with each passing decade. The only logical explanation was that the inner core itself was moving, rotating independently of the mantle and crust above. This phenomenon, known as inner core superrotation, suggests that the solid heart of our planet is spinning slightly faster than its surface, gaining about 0.3 to 0.5 degrees of longitude each year. The forces driving this are thought to be a complex interplay between the churning liquid of the outer core, which drags the inner core along with it, like a current turning a submerged stone, and the gravitational pull of the dense structures in the mantle, which tries to lock it in place. The result is a subtle, almost imperceptible differential rotation, a silent, cosmic heartbeat where the very center of our world has its own private day and night cycle. It is a discovery that transforms the inner core from a static, passive object into a truly dynamic player in the Earth's deep interior, a spinning heart at the center of it all. But the secrets of this strange world do not end with its independent spin. The seismic waves that pass through it have also revealed that the inner core has a distinct texture, a kind of planetary scale grain. This property is called seismic anisotropy. It means that the seismic waves do not travel through the inner core at the same speed in all directions. Specifically, they travel several percent faster when moving parallel to the Earth's axis of rotation, from pole to pole, than they do when traveling parallel to the equator. This gives us a profound clue about the inner core's structure. It suggests that it is not a simple, homogeneous lump of solid iron, but is instead a single, colossal crystal of iron, or at least is composed of many iron crystals that are all aligned in the same direction, with their grain pointing north-south. Just as it is easier to split a piece of wood along its grain than against it, it is easier for a seismic P-wave to travel along the aligned crystal lattice of the inner core. This makes our planet's heart not just a solid sphere, but a crystalline one, a jewel of unimaginable size and forged under unimaginable pressure. This discovery, like all others about this realm, is an act of incredible scientific delicacy, teased out from the faintest of signals. It relies on comparing the travel times of countless waves that have passed through the core at every conceivable angle, slowly building up a map of their speed variations to reveal the underlying structure of the material. And just when it seems we have a grasp on this crystalline world, new evidence emerges that adds yet another layer of mystery. The most recent studies of seismic waves reverberating within the inner core suggest that its anisotropic structure is not uniform. The very central part of the core, a sphere perhaps half the diameter of the whole inner core, seems to have a different crystal alignment, a different grain. This has led to the hypothesis of an innermost inner core, a distinct heart within the heart of our world, perhaps a fossil of an earlier stage of the planet's evolution. Our journey to the center has revealed not a simple final point, but a place of nested and layered wonders, a mystery that deepens the closer we look. We have found a world with its own texture, its own secrets, and its own silent, spinning rhythm, a beating heart of iron crystal that is the true, dynamic center of our living planet. To contemplate this place we have finally reached, this spinning, textured, crystalline world, nested within a churning ocean of liquid metal, is to be filled with a sense of profound wonder. But this wonder naturally leads to a deeper question. How did this magnificent and impossibly ordered structure come to be? How was the heart of our planet forged? To answer this, we must now undertake a different kind of journey, not one deeper into space, but deeper into time. We must rewind the story of our planet by 4.5 billion years, back to the very dawn of our solar system, to a time before the Earth was even a solid world. Let us imagine the scene. A vast, cold, and dark cloud of interstellar gas and dust, the solar nebula, swirling slowly in the emptiness of space. This was the raw material from which our Sun, our Earth, and all the other planets would be born. Slowly, under the patient, inexorable pull of gravity, the center of this cloud began to collapse, growing hotter and denser, eventually igniting to become our Sun. In the swirling disk of material that remained, an almost magical process began to unfold. Tiny grains of dust, no bigger than particles of smoke, began to stick together, first through gentle electrostatic attraction, and then, as they grew larger, through their own weak gravitational pull. These clumps grew into pebbles, the pebbles into boulders, the boulders into larger bodies called planetesimals, hundreds of kilometers across. And these planetesimals continued to collide and merge in a chaotic, cosmic demolition derby that lasted for millions of years. It was from this violent and random process of accretion that our own planet, the proto-Earth, was assembled. But this early Earth was not the world we know. It was a mostly homogeneous ball of rock, metal, and trapped gases, a jumbled mixture of all the different materials from the solar nebula, with no distinct crust, mantle, or core. The great transformation, the moment our planet truly began to find its form, was yet to come. The continuous bombardment by planetesimals and the decay of radioactive elements trapped within its interior generated an immense amount of heat, enough to cause the entire planet, or at least its outer layers, to melt into a global magma ocean. And in this molten, fluid state, a pivotal process known as planetary differentiation could finally begin. The different materials that made up the Earth were now free to move according to their density. The lighter silicate minerals, which would eventually form the mantle and crust, tended to float, while the much heavier elements, primarily iron and nickel, began to sink. Imagine a great, planetary-scale rain, but one that fell inwards instead of outwards. Droplets and streams of molten iron, heavier than the surrounding silicate magma, began to percolate and drip down through the body of the planet, drawn relentlessly by gravity towards the very center. This immense, planetary migration of iron, often called the iron catastrophe, was the single most important event in the formation of our world. As this colossal mass of metal fell towards the center, it released a tremendous amount of energy. The gravitational potential energy of the iron was converted into thermal energy, or heat, which raised the planet's internal temperature by thousands of degrees, making it even more molten and accelerating the process of differentiation further. This burst of heat from the formation of the core is a huge part of the primordial heat that the Earth retains to this day. And when this great iron rain finally reached the center, it pooled to form the dense, metallic core we have been exploring. Initially, this entire core would have been a single, turbulent sphere of liquid metal. But the story of the inner core, the solid heart, is a more recent one. As the Earth has slowly cooled and radiated its primordial heat out into space over the past 4.5 billion years, the very center of the core, where the pressure is greatest, eventually cooled just enough to reach the freezing point of iron. At that moment, the first iron crystals began to form. The seed of the solid inner core was planted, and from that moment on, it has been slowly, patiently growing, freezing solid from the liquid of the outer core at a rate of about 1 millimeter per year, a process that continues to this day. The solid heart of our planet was not there in the beginning. It is a child of deep time, a crystal that has been growing in the darkness for billions of years, a slow frozen memory of the planet's long, cooling journey. We have journeyed back in time to witness the birth of the core, a violent and fiery process of planetary self-organization that bequeathed our world its layered structure. And we have seen how the solid inner core is a child of deep time, slowly crystallizing as the planet cools. This brings us to a simple yet profound question. After 4.5 billion years of radiating its warmth into the cold vacuum of space, why is the Earth's interior still so intensely hot? Why hasn't our world cooled into a cold, inert ball of rock like the Moon or Mercury? The answer is that the Earth is not merely a cooling ember. It is a world with two hearts, two distinct sources of heat that have worked in concert to keep its geological engine running for eons. The first of these is the one we have already touched upon. The planet's primordial heat, the ancient, leftover warmth from its very formation. This is the heat of creation, a thermal inheritance from a chaotic past. Imagine the sheer violence of the Earth's assembly. For millions of years, planetesimals and protoplanets, some the size of small moons, slammed into the growing Earth. Their kinetic energy instantly converted into a tremendous blast of heat upon impact. This continuous, cataclysmic bombardment melted the rock and turned the young planet into a glowing, molten sphere. Added to this was the immense heat released during the iron catastrophe itself, as the gravitational potential energy of sinking iron was transformed into thermal energy, raising the planet's temperature by thousands of degrees. This vast reservoir of primordial heat was trapped deep within the planet when its surface eventually cooled and solidified to form a crust. And because rock is an excellent insulator, this trapped heat has been leaking out into space with incredible slowness ever since. It is like a colossal piece of iron pulled from a cosmic forge. Even after billions of years, its deep interior remains incandescently hot. This ancient fire, the fading embers of our planet's birth, still accounts for roughly half of the total heat flowing out of the Earth today. But this primordial heat, on its own, would not have been enough to keep our world so dynamic for so long. The planet would have cooled much more quickly. There must be another source of heat, one that is not fading away, but is being continuously generated, a fire that is still being actively stoked. This second source is the gentle, steady, and undying warmth of radioactive decay. The same primordial cloud of gas and dust that supplied the rock and metal to build our planet was also seasoned with a small amount of heavy, unstable elements, forged in the hearts of long-dead stars. These elements, such as uranium, thorium, and an unstable isotope of potassium called potassium-40, were incorporated into the Earth's mantle and crust as it formed. And these elements are radioactive, meaning their atomic nuclei are unstable. Over vast stretches of time, these unstable nuclei will spontaneously decay, breaking apart and transforming into lighter, more stable elements. Each time a single atom decays, it releases a tiny, microscopic burst of energy in the form of high-energy particles. These particles then fly out and collide with the surrounding atoms in the rock, and this collision, this atomic-level friction, generates a tiny puff of heat. One single decaying atom produces an infinitesimal amount of warmth, but when you consider the sheer quantity of these radioactive elements distributed throughout the Earth's almost 3,000-kilometer thick mantle, their collective effect is immense. It is a slow, steady, planetary-scale furnace that has been constantly producing heat since the Earth was born, and will continue to do so for billions of years to come. This radiogenic heat, the product of the slow, silent disintegration of atoms, accounts for the other half of the Earth's energy budget. And so, the fire in the heart of our world is a duet. The ancient, fading roar of the primordial fire of creation, and the quiet, constant, and enduring whisper of atomic decay, the faint, undying glow of stardust slowly releasing its stored energy in the deep, silent darkness. This enduring internal fire, kept alive by the twin flames of primordial embers and atomic decay, is more than just a geological curiosity. It is the ultimate foundation of our world's ability to support life. We have seen how its heat drives the geodynamo, creating the magnetic shield that protects our atmosphere. But its influence is even more profound, reaching up from the core to touch the very air we breathe and the climate that sustains us. The connection is a grand and elegant symphony of geology and biology, a cycle that operates on a timescale far greater than our own, known as the deep carbon cycle. Carbon is the fundamental building block of life on Earth. It is the backbone of every protein, every cell, every living thing. We are most familiar with its movement on the surface. Carbon dioxide from the atmosphere is absorbed by plants and plankton. It is eaten by animals, and it is returned to the atmosphere through respiration and decay. But this surface cycle is only one small, fast-turning loop in a much larger, slower, and more majestic system. This deeper cycle begins at the surface, where carbon is stored not just in living things, but in rocks. Over millions of years, the shells and skeletons of countless marine organisms, rich in calcium carbonate, sink to the ocean floor, building up thick layers of limestone. This rock-bound carbon is then carried along with the moving tectonic plates. When an oceanic plate is subducted beneath a continental plate, it carries this immense cargo of carbonate rock down with it, deep into the hot mantle. Here, under intense heat and pressure, the carbon is cooked out of the rock and incorporated into magma. This is the first half of the Great Cycle. The slow, inexorable removal of carbon from the surface and its burial in the deep earth. But for a planet to remain habitable, this carbon cannot be locked away forever. There must be a return path. That return path is powered directly by the planet's internal heat. The magma containing the recycled carbon, being hot and buoyant, eventually rises back towards the surface, and when it erupts from volcanoes, it releases the carbon back into the atmosphere in the form of carbon dioxide. This volcanic outgassing is the Earth breathing, a slow planetary exhalation that returns the essential building blocks of life to the surface, where they can be used again. This complete loop, from the atmosphere to the ocean floor, down into the mantle, and back out through a volcano, is the deep carbon cycle. And crucially, this cycle acts as a planetary thermostat, a natural climate-regulating feedback loop that has kept the Earth's temperature within a habitable range for billions of years. This elegant mechanism is known as the carbonate-silicate cycle. It works like this. If the Earth, for some reason, begins to cool down, volcanic activity, driven by the ever-present internal heat, continues to pump carbon dioxide into the atmosphere. This increases the greenhouse effect, which warms the planet back up. Conversely, if the planet begins to get too warm, the higher temperatures and increased evaporation lead to more rainfall. This increased rainfall weathers the silicate rocks on the continents more quickly, a chemical reaction that actively pulls carbon dioxide out of the atmosphere. This dissolved carbon then washes into the oceans, where it is used by marine life to form carbonate shells, which eventually sink, removing the carbon from the system for a geological age. This beautiful, self-regulating dance between the hot interior and the sunlit surface is what has prevented our world from freezing over into a snowball or boiling away into a runaway greenhouse. It is a direct consequence of living on a geologically active planet. The core's heat, therefore, is not just a passive feature of our world. It is the engine that drives the recycling of the elements of life and powers the thermostat that has maintained the stable, life-giving climate we all depend on. The very breath of our atmosphere is inextricably linked to the slow, fiery heartbeat of the deep earth. The connection between the fiery heart of our world and the delicate, life-sustaining breath of its atmosphere reveals a planet that is a single, interconnected system. The Earth's interior is not a separate, dead realm, but the very engine of its surface life. And this living planet communicates, not only through the fiery eruptions of its volcanoes or the slow grind of its continents, but in a much more subtle and all-encompassing voice, a deep and resonant hum that speaks of its own immense scale and substance. To hear this voice, we must listen not with our ears, but with the entire planet itself. When a truly massive earthquake occurs, one that ruptures hundreds of kilometers of a fault line and releases the energy of millions of atomic bombs, it does something more than just send seismic waves traveling through the Earth. It sends a shockwave so powerful that it sets the entire planet vibrating, like a colossal bell struck by a cosmic hammer. This phenomenon is known as the Earth's free oscillations. In the hours and even weeks following a great earthquake, our world does not just shake locally, it rings. The entire sphere of rock and metal begins to vibrate at a set of specific, resonant frequencies that are unique to its size, its density, and its internal structure. These are the natural notes that the Earth can play. And just like a musical instrument, our planet has a rich and complex harmony of these notes, or modes of oscillation. The simplest mode is a purely spherical vibration, where the entire planet rhythmically expands and contracts, breathing in and out over a period of about 20 minutes. Another fundamental mode is a torsional one, where the northern and southern hemispheres twist back and forth in opposite directions. And there are countless others, some where the surface moves in a complex checkerboard pattern, others where the entire sphere oscillates between being slightly flattened like a discus and slightly elongated like a football. These vibrations are, of course, far too slow and subtle for any human to feel directly, but they are clearly detected by our global network of sensitive seismographs, which record this deep, planetary ringing as it slowly fades away over many days. By studying the precise frequencies of these different notes, scientists can learn an incredible amount about the deep interior. Each mode of vibration samples the Earth in a different way, its frequency influenced by the density and elasticity of all the layers it passes through, from the crust to the very center of the inner core. These global oscillations provide one of our most powerful tools for understanding the planet as a whole, for they are the only signal that comes not just from the Earth, but of the Earth, a holistic vibration of the entire system. Perhaps most beautifully of all, our instruments have revealed that the Earth is never truly silent. Even in the complete absence of major earthquakes, our planet is constantly vibrating, humming with a faint, persistent, low-frequency energy. This is the continuous hum of the Earth. For a long time, the source of this mysterious, ever-present signal was a deep puzzle. But the leading theory now is that this hum is the sound of the ocean. As great ocean waves, stirred by distant storms, travel across the globe, they interfere with each other, creating subtle, long-period pressure waves that push and pull on the sea floor. This constant, gentle, and rhythmic massaging of the crust by the oceans is just enough to excite the Earth's natural resonant frequencies, causing the entire planet to hum, very faintly, all the time. And so, as our journey into the deepest mechanics of the interior comes to a close, we are left with this final, ethereal image. Our world, hanging in the silence of space, humming softly to itself, a deep, resonant chord generated by the slow, patient dance of its own blue waters, a living, breathing, ringing sphere whose song is a constant testament to its own vitality. This constant, gentle hum, the sound of the entire planet vibrating as one, serves as a beautiful and fitting transition for our journey. We have traveled down, kilometer by kilometer, through the layers of the deep Earth to arrive at its incandescent heart. Now, we begin our conceptual ascent, not by moving up through space, but by moving back through time, reflecting on what this journey into the planet's structure has revealed about its memory. For the Earth is not just a physical object, it is a geological archive, a library of deep time, and its layers are the chapters of its own 4.5 billion year long autobiography. Our descent to the core has been a journey back to the very first page, and as we return to the surface in our minds, we can now see the world not just as a place, but as a story. The core, both inner and outer, is the first and most foundational chapter, telling the story of the planet's violent birth. It speaks of a time of accretion and fiery chaos, of the great iron rain and the profound act of differentiation that gave our world its essential form. The immense heat it still holds is the lingering memory of that creation, a primordial energy that has powered the entire narrative ever since. Above it, the vast mantle forms the subsequent volumes, a long and patient story of slow, convective churning that has unfolded over eons. Its complex mineralogy and thermal structures are the records of countless cycles of rising and falling rock, of ancient continents being torn apart and reassembled, of ocean floors being born and consumed. It is the story of the planet's powerful, slow-moving engine, the author of all the drama that unfolds on the surface. And the crust, the thin, brittle layer we call home, is the most recent and intricately detailed chapter, the page upon which the story of life has been written. In its sedimentary layers, we find the fossilized remains of bygone ecosystems, and in its igneous rocks, we find the frozen records of the planet's wandering magnetic field. To contemplate the Earth in this way is to be confronted with the staggering, almost incomprehensible concept of deep time. Our own human lives, and even the whole of our recorded history, unfold on a timescale that is vanishingly small when set against the backdrop of the planet's story. If we were to compress the entire 4.5 billion year history of the Earth into a single calendar year, the first multi-celled organisms would not appear until sometime in November. The dinosaurs would roam the Earth for a couple of weeks in mid-December, and the entire recorded history of human civilization, from the ancient Egyptians to the present day, would occupy only the last 10 seconds before midnight on December 31st. The science of geology, then, is the art of learning to read this vast, non-human timescale. A geologist examining a canyon wall, with its layers of different rock, is like a historian carefully turning the fragile pages of an ancient manuscript, deciphering the language of stone and time to piece together the story of a lost world. Our journey to the core, then, has been a journey to the very anchor of this immense planetary history. Its formation was the event that set the entire narrative in motion. Its enduring heat has been the energy source driving the plot, and its profound weight and density have held the entire system together, providing the stable foundation upon which these billions of years of history could be built. As we float back up in our minds, away from the crystalline heart and the molten sea, through the slow river of the Mantle and the familiar ground of the crust, we carry with us this new perspective. The solid ground beneath our feet is not just a surface. It is the top page of a library of unimaginable depth and antiquity. To feel its presence is to feel a connection to this entire story, to feel our own brief, fleeting, and precious moment held within the grand, silent, and unfolding autobiography of a living planet. As we contemplate our world as a great historical archive, a story written in stone and fire over billions of years, it is easy to imagine this narrative unfolding in splendid isolation. But the autobiography of our planet, especially its first, fiery chapter, was not written alone. It was profoundly and irrevocably shaped by a cataclysmic encounter with a cosmic companion, an event so violent and so transformative that it not only forged the very heart of our world, but also gave birth to the silent, luminous partner that has graced our night sky ever since. Our moon. To understand the moon is to understand a pivotal moment in the history of the Earth's core, for their stories are one and the same, born from a single, ancient collision. The leading theory for the moon's origin, the giant impact hypothesis, is a story of cosmic violence and breathtaking creation. Let us return once more to the early solar system, about 4.5 billion years ago. The young Earth, having recently formed from the great iron rain that created its core, was still a glowing, molten world, a sphere of magma orbiting the Sun. But it was not the only world in its orbit. The hypothesis suggests that another protoplanet, a body roughly the size of Mars, which scientists have poetically named Theia, after the Greek goddess who was the mother of the moon, was on a collision course with our own. In a moment of unimaginable celestial drama, Theia did not strike the Earth head-on, but with a glancing blow, an impact of such colossal energy that it defies all earthly comparison. The collision would have vaporized Theia entirely, and it would have liquefied and blasted away a huge portion of the Earth's own silicate mantle, throwing a cloud of incandescent rock and gas into orbit around our wounded planet. For a time, the Earth would have been surrounded by a brilliant, glowing ring of debris, a structure perhaps like Saturn's rings, but made of superheated magma. But this ring was not destined to last. Over a remarkably short period of time, perhaps only a few thousand years, the relentless force of gravity began to pull this material together. Clumps formed, merged, and grew, until the entire ring had coalesced into a single, large, spherical body, our moon, born red-hot from the vaporized remains of two worlds. This elegant theory explains so many of the strange features of the Earth-Moon system. It explains why the moon's composition is so similar to that of the Earth's mantle, and why it is so depleted of the iron that should be at its center. It was formed mostly from the mantles of the two colliding bodies, after their own iron had already sunk to their respective cores. It explains the unique orbital mechanics of our system, and why the Earth spins faster than it otherwise should. The consequences for our planet and its deep interior were profound. The sheer energy of the impact would have added a tremendous amount of heat to the young Earth, ensuring its outer layers remained a molten magma ocean for millions of years, and accelerating the final stages of core formation. This event likely blasted away any primordial atmosphere the Earth had, forcing our world to create a new one through subsequent volcanic outgassing. And perhaps most importantly, this great collision is what is believed to have knocked our planet over, giving it its characteristic axial tilt of 23.5 degrees, the gentle tilt that gives our world its seasons. And in the eons since that fiery birth, the moon has been far more than a passive ornament in our sky. Its significant gravitational presence has acted as a vital stabilizing anchor for our world. It has prevented the Earth's axial tilt from wobbling chaotically over time, which would have led to wild and unpredictable swings in climate. The moon has held us steady, ensuring the long-term climatic stability that has been so crucial for the evolution and survival of complex life. And so, when you next look up at the pale, silent face of the moon, you can see it not as a foreign object, but as a lost piece of our own world, a constant, luminous reminder of the cosmic violence that forged our planet's fiery heart and gave us our gentle, life-sustaining seasons. We have journeyed from the solid ground beneath our feet to the spinning, crystalline heart of the planet, and from there to the cosmic collision that gave us our moon. We have travelled through space and through time, listening to the scientific story of our world's deep interior. And now, for this final stage of our reflective ascent, let us make one last turn, the most intimate of all, the turn inwards. For this entire journey, this exploration of the layers of a planet can also be seen as a beautiful and powerful metaphor for the exploration of the layers of our own selves. The quest to understand the world and the quest to understand the self are, perhaps, not two different journeys, but one and the same, each reflecting the other in a deep and resonant mirror. Let us imagine, just for a moment, that the geography of our planet is also the geography of our own minds. The sunlit crust, with its familiar landscapes, its cities, its forests, and its oceans, is like our conscious awareness. It is the part of ourselves that we know, the realm of our everyday thoughts, our plans, our conversations, and our immediate perceptions. It is the world we inhabit daily, the surface upon which we live our lives. We can map it, we can name its features, and we can feel, much like our ancestors did, that this surface is all there is, that this conscious awareness is the entirety of our being. But our journey has taught us that this is just the thinnest of skins. Beneath this conscious crust lies the vast and mysterious mantle, a realm which we can compare to our own subconscious mind. It is a world far larger and more powerful than our conscious awareness, a place of deep, slow-moving currents of emotion, memory, instinct, and intuition. We cannot see it directly, but its movements are the hidden engine that shapes the landscape of our conscious thoughts and feelings. The pressures and tensions that build up within it can give rise to sudden emotional earthquakes, or moments of volcanic inspiration where something from the deep breaks through to the surface. It is the repository of our entire life's experience, of the ancient, inherited patterns of our species, a warm, dark, and flowing world that holds the secrets of who we truly are. And at the very centre, we find the core, a perfect metaphor for the deepest, most essential part of ourself. It is the source of our most fundamental energy, our vitality, our will to live. It is a place of immense heat and pressure, the seat of our deepest identity, forged in the fires of our earliest experiences. This inner core, like the solid crystal at the heart of the earth, is our anchor, the unshakable centre of our being. And the liquid outer core that surrounds it, the source of the magnetic field, is like the energy that radiates from this centre, creating the atmosphere of our presence, our personal energy field that protects us, defines our boundaries, and shapes how we interact with the world around us. Our journey to the centre of the earth, then, can be seen as a journey of introspection, and the science of seismology is like the practice of mindfulness. It is the art of sitting in stillness and listening to the faint vibrations of our own inner world, learning to map our own depths, not by sight, but by feeling the echoes of our own heart. In this light, the human need for grounding, for a feeling of connection to the Earth becomes something much more than a poetic phrase. It is perhaps a deep, intuitive recognition of this metaphorical truth. To feel the solid Earth beneath us is to feel a connection to our own deep, unwavering center, to draw strength and stability from that which is ancient, vast and true, both outside of us and within us. The journey to the heart of the planet reveals a world of profound wonder and complexity, and it also gifts us a new language for understanding ourselves. It reminds us that we, too, are layered beings with hidden depths and unseen energies, and that the exploration of these inner landscapes is the most rewarding journey of all. Our journey to the heart of the planet, and our parallel journey into the heart of the self, has shown us a world and a psyche defined by their deep, unseen, and life-giving energies. The core is a source of immense and enduring power, a fire that has kept our planet vibrant and alive for billions of years, allowing it to become a rare and precious haven for life in the vastness of the cosmos. But the laws of thermodynamics are universal and inescapable, and no fire, not even the great, slow-burning fire at the heart of a world, can burn forever. Our planet, like all things, has a life cycle, and to contemplate its distant future is not an exercise in fear, but a final, profound lesson in perspective and the beautiful, melancholic grace of cosmic time. The story of the Earth, since its formation, has been one of continuous, albeit incredibly slow, cooling. The combined heat from its primordial formation and its ongoing radioactive decay is not quite enough to balance the heat that it constantly radiates away from its surface into the cold of space. The planet's overall thermal budget is in a state of deficit, losing a tiny fraction more energy than it generates. As a consequence, the deep interior is, degree by imperceptible degree, cooling down. We see the evidence of this cooling in the slow growth of the solid inner core, which continues to expand by about 1 millimeter each year as the liquid iron of the outer core crystallizes onto its surface. And the story of the Earth's very distant future is the story of this process continuing to its ultimate conclusion. Let us now travel forward in our minds, across a span of time as vast as the one we have already traversed. Billions of years from now, our sun will still be shining, but the Earth beneath it will be a profoundly different world. The relentless, slow cooling will have continued, and the solid inner core will have grown ever larger, the frontier of its crystallization steadily advancing outwards through what was once the molten sea of the outer core. Eventually, a day will come when the last of the liquid outer core freezes solid. The entire metallic heart of our planet, from its very center to the Gutenberg discontinuity, will be a single, solid sphere of iron and nickel. It will still be hot, but it will be static. And in that moment, the geodynamo will die. With no moving, conductive fluid to power it, the great planetary engine that sustained our magnetic field for eons will fall silent. The magnetic field itself, our luminous, protective shield, will decay and vanish, and the Earth will be left naked and exposed to the harshness of space. To understand what this means, we need only look to our celestial neighbor, Mars. The red planet offers us a gentle, silent preview of our own world's deep future. Mars is a much smaller planet than Earth, and so it had less primordial heat to begin with, and a smaller volume to contain heat-producing radioactive elements. It cooled much more quickly. It once had a liquid core, a geodynamo, and a protective magnetic field. It had a thick atmosphere, flowing rivers, and perhaps even shallow oceans. But as its interior cooled and its core solidified, its magnetic field died. And without that protection, the relentless solar wind swept in, and over hundreds of millions of years, stripped most of its atmosphere away, turning a once warmer, wetter world into the cold, barren, and breathtakingly desolate planet we see today. This is the long, slow, and inevitable path that awaits our own world. The fading of the core's fire will lead to the silencing of the geodynamo, the loss of our atmosphere, and the boiling away of our oceans. But this is not a story of doom. It is a story of a planetary life. It is a reminder that we are living in a precious and privileged moment, a geological noon when our planet is in its vibrant, dynamic prime. The end of this story lies in a future so impossibly distant that it defies our comprehension. To know that it will come is simply to understand the full arc of our planet's existence, to see its life as a complete and beautiful story, and to feel an even deeper sense of gratitude for the warmth, the protection, and the life that its fiery heart provides for us, right here, right now. We now let our awareness drift back from that impossibly distant future, back from the silent, ruddy plains of a long-dead Mars, back through the billions of years to this present moment, to the here and now. Let us return to the simple, quiet sensation that began our journey. The feeling of the ground beneath you, the gentle, solid presence of the earth, holding you as you rest. After our long journey to the heart of it all and back, this feeling is no longer the same. It is no longer a simple, inert foundation. It is the surface of a story, the skin of a living world, imbued with a new and profound depth of meaning. The ground upon which you rest is the roof of a hidden world, the final, sunlit layer of a planet whose true wonder lies in its unseen depths. It is a surface that is carried upon the slow, majestic currents of the Mantle's river of stone. And this great river is driven by the steady, patient heat radiating from a captive star at its center, a solid crystal of iron hotter than the sun. This solid heart is, in turn, suspended within a churning, metallic ocean, whose violent, swirling dance generates an invisible, protective shield of energy, a luminous guardian that deflects the solar winds and allows our world to keep its precious, life-giving atmosphere. And it is this shield that, in the polar nights, catches the breath of the sun and paints the sky with the ethereal, silent fire of the aurora. The journey has revealed to us a breathtaking chain of connection, an unbroken line of causation from the spinning crystalline heart at the center of the world to the very air you are breathing. Right now, in this quiet moment, our journey has taught us that our world is a single, deeply interconnected system. The slow decay of a single radioactive atom in the mantle can contribute the tiny puff of heat that, when multiplied by trillions, helps to drive a continental plate, which in turn raises a mountain range that will alter the weather for millennia and shape the course of evolution on its slopes. Nothing is separate. The deep past is alive in the present, in the primordial heat that still warms us, in the ancient continents whose outlines we can still see in our modern world. And we, too, are a part of this system. We are not merely living on the earth. We are an expression of the earth. Our bodies are built from its elements. Our lives are powered by its energy. And our consciousness is, perhaps, the universe's most beautiful way of understanding itself. To know the story of our planet's heart is to feel a deeper sense of being at home in the cosmos. It is to understand that beneath the sometimes chaotic and noisy surface of our world and our lives, there are deep, slow, and powerful currents that are moving us, ancient rhythms that are shaping us. There is a solid, stable center that holds us. And so, our long journey to the heart of the planet is now complete. We have returned to the surface, but we see it with new eyes, with a deeper appreciation for the silent, fiery, and magnificent world that lies just beneath our feet, and whose steady, life-giving presence makes all of our quiet nights and sunlit days possible. Thank you for joining me on this gentle exploration. And now, there is nothing left to do but to let these stories and images go, to allow your mind to be as still and quiet as the deep mantle, and to drift into a peaceful and restorative sleep held safely by the silent, humming, and ever-present heart of our world.